introduction. Thanks very much for organizing this event. I know you've been working very hard every weekend to have a very insightful discussion with the speakers, and I really appreciate that. And I really appreciate all the people that showed up this Sunday to watch our talk. So yes, I'm currently a postdoc at UT. I work with Professor Nanshu Lu, and but this talk will be about my PhD research in Professor K.G. Zhao's group at Purdue. And my goal here is to show how, using new experimental techniques and new materials, we can develop a new understanding of old theories. So chemomechanics, that's an old field, but it was revived with energy storage. And we've been learning through the advanced technological advancements, we've been able to understand much better some of this fundamental phenomena regulating those systems. This background image is an image that I took at the very early beginning of my PhD. It's a little misleading because this is a composite material and I was doing some indentation, and you can see the cracks and the crack in this very intricate pattern. But today I'll be just covering thin film, so it will not have like very pretty pictures like that. But I promise it will still be interesting. So I'll start with the very basics. For my application, I'm studying lithium-ion batteries, although the concepts here are very general. So in those systems, the energy storage happens through the shuffling of ions between two electrodes. So there is three main components. You have two electrodes; they are connected through an external electrical circuit to a load or a power supply, and they are separated by a electrically insulating liquid, but that can conduct ions. So inside the system, the ions can move from one electrode to the other, and to achieve net charge neutrality, the electrons will move in the external circuit, and that's how we get the power for the batteries. The trick here is that you want to accommodate as many ions as you can in the host material. The more ions you can pack in there, the more energy storage specific capacity you have. The trade-off is that the more lithium you can you try to pair in with the host, the more the host will have to expand to accommodate those new chemical species inserting in that material. So here there is a variety of different types of materials for anodes and cathodes for lithium-ion batteries. They have all different structures, but the trend is very clear. The more lithium you want to pack, the more volume expansion you have to accommodate. And if there was no constraints, that wouldn't be a problem. It would just freely expand and shrink, right? It would cycle. However, there is many reasons why those chemical strengths, they might be constrained. There could be some geometrical constraint from the electrode itself, from the package, but there is also the kinetic limitation. So here's one example where you insert some ions inside this host lattice, and because there is not enough time for those ions to homogenize, you will get compressive stress on one side and like a tensile stress on the other side. So this stress field, it's created from the kinetic limitations. And those stress fields, then they will just intrinsically happen in the batteries inside those solid materials. And they can have very wide ramifications. So one problem that can happen is that they can lead to structural degradation. So here's an example of a particle. As it is being lithiated, you can see huge cracks that form, pieces of material that detach. This is, of course, very bad for the battery performance. And over cycles, they accumulate, and then that's one of the reasons why the battery loses capacity over time, and then you cannot really reach it's like unusable after some point, right? So this is one thing that can happen, but another that is a much more fundamental aspect of the effect of mechanics on the chemistry of the battery is that stresses, the strain energy will regulate the energy barriers and the driving forces for the reaction, charge transfer, and diffusion in those systems. So here's one example that I really like. It's an experiment that's quite intuitive. You have a germanium nanowire that is in contact with lithium electrolyte here. And if there was no stresses, this lithium would propagate through the entire surface at the same time. However, if you apply a bending stress to this wire, so this wire here is kind of bended on this way, the side under tension will lithiate faster than the side under compression. This is for germanium. So there is many reasons why this can happen. But studying this interplay between chemistry and mechanics has been a lot simulation-based or very qualitative experimental. So like in this case here, you have an SEM, you don't really know what's the concentration at any point. You just have a qualitative understanding of what's happening there. So we really need to go and try to expand our techniques so we can probe those systems in a much more detailed way. But one thing also to notice is that here we are applying a external stress, but like I said, as part of the operating principle of the battery, you're going to have those stresses that come up as a function of the kinetic limitations, and those stresses on the other hand will then affect the kinetics. So it is a mutually regulating effect. So understanding this regulation is one thing that we're very interested in studying. So that will be one part of my interest. The other part of this work is the fact that as you lithiate those materials, they are changing their composition. Their mechanical behaviors are also changing. So if you characterize the material in the pristine state, it's not the same material as after lithium has been inserted. It's a different material. So the material has this dynamic composition. So in a pristine state, the material might be very brittle. When it's lithiated, it might be ductile. So it can change completely. So we need to find a way to have this more complete understanding of the mechanical behaviors of the materials as well. So, and please feel free to interrupt me anytime. I might not see your hand, but if you send a picture or send a comment, I will probably be able to see in the chat. So first I will start with how do we characterize those materials, do mechanical probing of those materials. So the challenge, in addition to the fact that the composition is changing, we have the fact that those characteristic scales of those materials, they are very small, micrometer, sometimes nanometer size. And once you start to lithiate them, they become very sensitive to moisture and oxygen. So they're a closed system, you cannot really open it in the air and to test it. So for that reason, we integrated this platform to study specifically these active energy materials. The platform is, we use nanoindentation to probe the materials, but this nanoindenter is inside a glove box with inert gas so that we can have the cell that holds the electrodes opened so that we can access the electrodes with the nanoindenter indent inside the cell. At the same time, this indenter is inside the electrolyte so that it can allow the cell to that's why we call it operando indentation, because we allow the cell to operate and we allow the reactions to take place here. At the same time, this is connected to a potentiostat so that we can control the rate of the reactions. And that would be very handy. So this is our study. The results that I will present today will be on amorphous silicon electrodes. This is just one material that you can study with the system. The reason that I chose this is because it's there is a couple of reasons. One, it's a material that changes a lot the composition. It goes from pure silicon to 4 times as much silicon as you have lithium as you have silicon in the lithiated state. So it would change. We can expect a lot of change happening. It is there is a commercial interest in this material. There for a long time, companies have been trying to make this material commercialized as an electrode, as an anode material. Right now, we just use small amounts, but the goal is to use pure silicon electrode, and that is a little bit harder because of the mechanical problems. So it has a very meaningful motivation there. You can see here the preliminary other results that show that the Young's modulus of this material will vary very much with the lithium concentration. And there is also the fact that the kinetics of the system was kind of an open question. There was a lot of debate on why it behaved the way it does. So here's one video of the lithium, the amorphous silicon being lithiated. You can see the top area here is where the lithium is coming in, and it's expanding. But interestingly, you see this very sharp interface between the lithiated and unlithiated regions. And that is that's kind of surprising because this is not a phase transforming material. You have amorphous and amorphous. So you would generally expect a more smooth transition there, because if it would be a diffusion limited process. But another experiment, they see a similar thing where there is a sharp interface during the lithiation, and then during the delithiation there is no sharp interface. So it's quite odd, this material. So there was a lot of debate. I said, okay, let's see what is going on here. So I will start with the mechanical characterization. So first, our goal will be to characterize the relationship between mechanical property and concentration. With nanoindenter, we can measure many properties. Here, I'll give the example of elastic modulus. This is the schematic of our cell. We have a silicon film, the lithium metal, all inside the electrolyte. We are controlling the current that goes from that is extracted from the cell. Because we know the capacity, we know the current. At any time, we know how much lithium must have inserted inside that silicon. So this is what's happening. Because it is a film, we are slowly charging it. This entire film is lithiated at the same rate. We can assume it's homogeneous. Because that it's homogeneous, what do I do? At the same time that it's lithiating, I'm going to indent that sample. Each indent, I will get a point on my property versus concentration curve. So here, if I repeat this many times, I will have this relationship between the elastic modulus and the lithium content inside the silicon. So this is the first step. This is I do this for, and I measure 3 different things at the same time. It's something you can extract from the experimental data: modulus, hardness, and stress exponent as a function of the composition of the silicon. It goes from 0 to about over 3. So you can see that, first of all, the trend is very different depending on the property. For instance, for the stress exponent, a little bit of lithium you put in, it becomes much creepier, and then nothing more happens. While for elastic modulus, it's kind of this slow change, more like a rule of mixture between pure silicon and pure lithium. And this was a lot of work. If people are interested in actually reproducing this, you have to look at the paper, because there was a lot of little details we have to address. For example, the fact that the sample is expanding at the same time that we're indenting, the fact that can form surface fumes on top of the sample, cracks, all those sorts of things. We had to address those. And once that's addressed, you can see that it's very robust, actually. I can charge it really slow. This C/10 means that it took 10 hours for me to charge. Can charge it more faster. I still get the same consistent data independently of how I charge. So this is kind of the intrinsic relationship between the property and the composition. This is useful for you to model those systems. You can model the stress, how it generates in a particle, by having this constitutive relationships between stress and strain. But that's not all. We need to look at the kinetics, and that's a little bit more complicated. So this is kind of a very different path that we took. We are trying to profile the chemical composition of the sample through our knowledge of this mechanical property and concentration relationship. So this is what I've done before. I know the relationship between the modules and concentration. Now what I'm going to do next is a different setup of the experiment. I will have my silicon film in contact with lithium just on one side, such that the lithium will spontaneously, because it's in contact, the lithium will start migrating toward inside the silicon. The rate of this migration, it depends on the properties. If the diffusivity, or if it's reaction limited, it would be like the reaction constant. But we don't know yet, right? We just know that there will be this inhomogeneous distribution. There is no way for me to probe this. If I try to probe using EDS or some spectroscopy technique, that's tricky because lithium is a very light element. You don't usually catch it. Usually what we do is we do some indirect way, like, but those really require synchrotron techniques. It's a very intensive, lab-intensive process. So what we're gonna do is, and in addition, this is amorphous material, which is even more challenging to probe. So what we're gonna do is we're going to use the modulus knowledge. So here I have this distribution. I don't know what the concentration is at any point. I will go with my indenter and I'll perform one indent at each point. At each point, I will get a modulus. I will do this repeatedly throughout the sample, and I have this distribution of mechanical properties, which is not constant because the concentration is different everywhere, but this on itself is not useful for me. I want to know what the concentration is. But from before, I already know this relationship here. So what do? I take the modulus and I input it into the inverse of this function here. And what I get is the concentration distribution in the sample. And I can repeat this many times and I will get the evolution of that concentration distribution. And this is what is going to really help us to characterize the kinetics. And then later on, we're going to study the stress effect. So this is the approach that we've done to characterize the concentration. So here's a film of the silicon being lithiated. The lithium metal is on this side. You can see visually in the optical image this propagating front. But like I said, I don't know what the concentration is. So I perform those arrays of nanoindentation. Here's one example. This is the elastic modulus and the hardness as a function of the distance from the lithium metal on one side. And you can see it's very inhomogeneous. And at the interface, you can see a really big jump where it goes from a much lower value to a much higher value. Using the function that I have before, I can get, like I explained, transform this elastic modulus or this hardness into a concentration profile. So this is the spatiotemporal composition map that I perform. So basically what I'm seeing here is how the concentration distribution evolves with time. And first of all, we can see it's more or less the front propagates as a function of the square root of time, which means it's likely a diffusion limited process. So we're going to model this as diffusion. And with this, you can see also that this profile here is very concave, very different than what you would expect from a model where you have a constant diffusivity. So there is this very classical model called Matano-Boltzmann that if you have, this equation here is, I imagine you've probably seen it before, it's just Fick's law. So the flux is a function of the diffusivity times the gradient in concentration. You can integrate this to get what is the diffusivity as a function of concentration. So for each profile, I integrate this, and they should, if it is a diffusion regulated process, they should all overlap, because it means that this equation can explain this phenomenon. So this process, we get this nice overlap. Independent of how we measure it, we find that the diffusivity is very low at low concentration, very high at high concentration. So this is why we get this very sharp interface here, because the lithium can diffuse really fast, orders of magnitude faster in the lithiated silicon. But the silicon diffusivity, to break that, it's a bottleneck. So it accumulates and piles up at the boundary, and that's why we see, even though it's a diffusion limited process, you still can get a sharp interface just because of the shape of the diffusivity. So if I, let me see how I am with time. I'm a little over time.
Yes, a little bit. 5
Okay,
minutes,
I will
yeah.
just a little. I will just wrap up. So, what I find out is that this equation really doesn't explain this behavior in all boundary conditions. If I change the boundary conditions, then my results didn't match. So what I had to do is I had to consider the more complete method, which is an old method, Larcher-Kahn method, which includes the stress gradient as a driving force in addition to the chemical driving force for diffusion. When if I consider this, the fact that I know the mechanical properties and the distribution of lithium, I can back calculate what is the property that I really care about, which is the intrinsic diffusivity. With this intrinsic diffusivity, I can model the stress effect and decouple it from the chemical driving force for diffusion. And I can even quantify which one is higher. In this case, the chemical diffusivity is much higher. The chemical driving force is much higher than the mechanical driving force. But the mechanical driving force is still significant. So just to wrap up, I will show you kind of what was interesting is that we had this experiment. We're not really looking into reproducing this. We didn't think that our results would give this, explain this behavior. But interestingly, it does. Just by the fact that the diffusivity is varying with concentration, we had this sharp interface. So here's the lithiation, the concentration font going really sharp during lithiation, but during delithiation, very smooth. Doesn't really have that effect. So this is what matches this experiment. And also what we find interesting is that I didn't even notice this before, but you can see that it takes 100 seconds for this particle to lithiate. But it takes more than 1,000 seconds to lithiate, and it doesn't even go back to the original shape. And that's exactly what our experiment shows. The lithiation happens much faster than the delithiation. So there is an asymmetry in the rate of the charging of the battery just because of the diffusivity. So that's all I wanted to talk about. So if we have a platform to study mechanical properties, we have a platform to study kinetics, all based on mechanics. So this is the power of our community. We can kind of really inform the chemistry of the systems. And then we found a bunch of new understanding of the processes regulating those systems through that. Thanks, and I'm really sorry for the delay.
Thank you, Luize.